I would like to start by thanking Constantino, Marcus, Czeslaw, and all the other organizers and people involved for sticking to it, trying to organize an in-presence meeting. And there's actually quite an audience here. I doubt the people on the screens in their homes or institutions can actually see the almost full lecture hall. And I'm enjoying this very much. And also, this is a picture of my team just at a recent, the first outing after a long confinement to homes and offices. And I would like to talk about a topic that in fact picks up on the last question we just had. Sort of where are there possibilities, or are there possibilities to go beyond quantum mechanics? And we've been doing for quite a while, as most of you probably know, precision interferometry tests of quantum mechanics. And rather than in the spirit of what can we do in a technology sense, are there things we don't know well enough? And this is not about gravity at all. And just after me, Ubershi Sinya from Raman Research Institute will speak on, I hope, similar topics. And so the two themes that I want to convey today are all based on the same set of experiments. The first is what we call the Sorkin tests for higher order interference. And this goes in the direction of how well do we know Born's rule, or is there space in nature or the possibility of interference that goes beyond what we would expect from quantum mechanics. Obviously, if there was producing a lot of extra problems in theory and experiment, but it never hurts to ask and to look very closely. And the second one, sort of inspired, in fact, by the first one, is on tests for different types of fields of representations for quantum mechanical wave functions, testing for quaternion quantum theory, which was proposed by Asha Perez a long time ago. And these, it turns out they have similar requirements. And so my talk is going to be, in the most part, a talk about systematic errors. This is somehow interesting and also boring, perhaps, about precision experiments, because whatever you do, you will only always get to the next step and find sort of the next problem in the experiment. And so this is a bit about an evolution of a series of experiments, and with some very recent results, in fact. All right, so let's start with the first thing, the Sorkin tests. And I will take you back to extremely simple thing if you don't think about very carefully, which turns out to be a bit more problematic than you might have thought. And that is that, of course, in quantum theory, and in fact in every, I guess, wave theory, we have a superposition principle in that different solutions of a differential equation can be superposed and form another solution in the way that we see it in, for example, the double slit, where there's two possibilities for a particle to evolve to the detector or screen, and then we take a coherent sum of two amplitudes, psi A and psi B. Of course, these should be orthogonal, ideally, and then the superposition principle would hold. And of course, as we already see indicated here on this picture, we would expect interference. And so we can ask, what is interference? And in the sense of Raphael Sorkin, interference is what goes beyond sort of the classical or the non-wave theory probabilities. And I apologize for the really tiny labeling here. I prefer to view this in terms of interferometers rather than slits. I find it a bit easier to think, in fact. So here we have a Mach-Zehnder interferometer, and with particles coming in somewhere, and a detector monitoring at least one output. And we can look at three different scenarios here where both paths are open, but we can also block 1, block path B, or block path A, and then we can identify our interference term that, of course, arises from absolute squaring our superposition here as the thing that is missing if we want to know the probability for the both open case from difference from just adding the two sort of individual probabilities here. And so in turning this around, we could also define, without sort of referring to an underlying theory as quantum mechanics in a generalized probabilistic frame, we can just define the interference term as that what is missing between these different experiments, or as different realizations of in a similar apparatus. Okay, and that of course is all known, and it gets a bit more interesting, but also very simple, of course, if we go to 3 paths and now square the superposition of 3 amplitudes, and we see that by the Born rule or the square law, all interference terms are in fact binary interference terms. So it is said that interference in fact occurs in pairs of paths, and going sort of way back, there's, unless you have the square law, there's actually no reason why it should be so. You know? Why should it be only pairs? Why not something else? And so of course we get these interference terms, and let me just rearrange this a little bit, expand by the definition I just gave for each of these interference terms, and then reorganizing a little bit, and we find that the 3-path probability is entirely defined by the 2-path probabilities and the single-path ones. And now I can ask, well, is there something beyond that? Is there something like the interference we had in going from single to 2 paths, when we now go from single to 2 to 3 paths? And this is basically what Raphael Sorkin proposed in a program, I would say, that was trying to categorize probabilistic theories and how they deviate from classical physics. So he defined a second-order interference term, which I called IABC here, as the difference of this 3-path probability with minus, so there's minus the 2-path and plus the single-path ones. And needless to say, you can see it from the equation here in orthodox quantum mechanics. And as far as we know in nature, this would be identically 0, because obviously this 3-path is already defined by this. So this is just, in fact, giving us an experimental tool, because we can now set up a null experiment by measuring all 8 possible combinations, if we include the one where all 3 slits here in the slit picture again are blocked, defining our background, if you will, and we can measure this quantity and see if it's 0. And what's very nice about this is it doesn't matter how the amplitudes are, how large they are, these slits or interferometer paths can all be different. And in fact, the shutters don't need to be perfect. Whatever you do, this will be 0 if your experiment, if nature follows Born's rule. Except, of course, for systematic errors, as we'll see in a bit. And then you can choose to normalize this, because I guess it's a little tricky. Experimentally, we never measure real probabilities. We can sort of divide by the particles that go into the interferometer, but that's rarely known, and there's a lot of loss, so this would be somewhat artificial. And we chose some time ago to normalize by the expected interference, because if you had a theory that showed no first-order interference, Sorkin says that you would also see no higher-order interference by definition. In that sense, this is a bit of a quality parameter. And we published a slit experiment a long time ago with Ubushi, and I never really liked the slits so much. She does much more. And I realized a bit later why, and in fact, Ubushi also showed formally why this is a problem, and that is if you block a slit, it's not an innocent thing to do. In fact, you're changing the boundary conditions of your wave field, and then the superposition principle doesn't apply. And in fact, Ubushi calls this naive application of the superposition principle, where a blocked slit in fact influences what happens elsewhere. And one way of viewing this is by realizing that, of course, all in the Feynman path approach, you have to include non-classical paths where the particles loop back through the slits. And now, of course, it does make a difference for an AB measurement whether C is open or not. So, in fact, you have manifest apparent higher order interference in such an experiment. And obviously, this will also reduce exponentially by increasing the slit separation. And if I now do this in the Mars-Ende interferometer, where the arms are separated by, I don't know how many 1,000 or 10,000 wavelengths, then all of these exponential terms are ridiculously small and will not matter anymore. And in fact, I have space to put my shutter in, which is much easier than with the slits. All right, and so we came up with this 5-path interferometer. It had 5 for some technical reasons, but it also turned out to be quite useful. In fact, you can go to higher orders, measure not only a 2nd order, but also a 3rd order, a 4th order interference term. It also has the advantage that there's many, in fact, there's 10 3-path sub-interferometers in here, which lets you sort out some systematics, because if something goes very, very wrong, you would usually see it show up in multiple combinations. And we did this in a variety of ways. And I'm not going to talk about it long because this is old, with single photons and also with just with laser light. Effectively got bounds on this interference on the order of 10 to the minus 4. And the main deviation that we still see in this picture, in fact, comes from detector nonlinearity. We're trying to show that Bohn's rule is right, so that the probability is a proportion of psi square. But if the detector doesn't respond to psi square, but has some correction because it saturates, or because there is dead time, or some other nonlinearity, then that will show up as an effective nonlinearity and give you effective or apparent higher order interference. And so once we compare to that model, this is in fact the what we get, again, something like 10 to the minus 4. And in fact, in most cases, this is actually limited by how well we can determine that nonlinearity of the detector. Okay, which is in itself not so easy, because detectors are in fact quite linear, but then you have trouble estimating those parameters very precisely, and then doing that comparison. And I should also say that, of course, a lot of other experiments have been done too. I should point out, especially, I think, Joachim van Santi's group in Erlangen, who've looked into higher order interference of multiple particles. And there's some very interesting questions about, if you do this with 2 particles in an interferometer, at what order can these higher order interferences show up in principle? I think that's an interesting option. Sure.
I mean, you said that you wanted to show that there are only the quadratic terms. Wouldn't the more correct philosophy be to find out how large the other terms maximally could be? And in that sense, my question would be, according to your experiments, how large could they be compared to the quadratic terms?
Yes, very good. In fact, I think that's in one of the papers. It depends, of course, on how you model this. You could go to, I guess, psi to the 3rd, psi to the 4th, and then put bounds on the coefficients there. And in fact, I think this quantity very directly maps into these things. So any sort of next higher order term would have to be sort of about 10 to the minus 3 smaller than which is a rather loose bound. So as an experimentalist, I'm not happy about this. It should be 10 to the minus 27 or something, you'd think, but we have to come up with better experiments. In fact,
suppose it would have been 10 to the minus 3 in nature, you would not have seen it.
I guess
smaller than 10 to the minus 3.
I guess. Which is, and that's discomforting, no? or well, you could say I'm excited because there is a possibility, but realistically, you would think that it would have shown up somewhere else. And in fact, that's a question I often get on this. Wouldn't we see this in scattering cross sections, whatnot? And it turns out it's very hard to do this quantitatively. And here it works because it's a null experiment. Whereas in all other things, if you try to do precision diffraction or something like that, you have no chance. All right, and so the conclusion is why is the precision not better here? And the main limitations really phase fluctuations in the free space interferometer, and that's why we thought, okay, if it's probably the air and whatnot. I mean, there's some phase stabilization in here. The drift is very slow, but still there's some fast fluctuations that will average out. So they will not give you a bias, but they give you a large uncertainty bar. And so we decided to go to a waveguide interferometer, which is a fused silica chip with laser-written waveguides. I will introduce the technique in just a bit, and have actual holes through these waveguides where you can stick a wire in to close the path. And I was hoping for a more technical, a more modern approach. On the other hand, this has a very concrete shuttering mechanism. And in fact, it will turn out a bit later in the talk that the quality of shuttering is not so important here for the Sorkin tests, but for the Paris tests, it's essential that there is no light going through. And it will surprise you that quite a bit of light, or more light than we thought, actually goes through these steel wires. What's also surprising is that there's hardly any loss for the light going through that hole, because we fill the hole with index matching oil, and the waveguides have very low numerical aperture, so they're very large. It's almost like a plane wave, and the hole hardly disturbs the propagation when there is no steel wire inserted. This is a 60 micron square hole, and a 50 micron steel wire, and the waveguide's about 10 micron in diameter. All right, and these are actual tritters. That was also something we preferred. So a mass sender interferometer that is defined by 3 couplers, where these waveguides come very close to each other, and by tunnel coupling they exchange energy, and so we actually have a symmetric tritter here at the input and a symmetric tritter at the output. Unfortunately, and this is the big drawback, there is no way of changing phases here. Okay, so we're confined except by changing overall temperature of the chip to a fixed point in phase space, which is not a problem for the Sorkin tests, but is a problem for the Perez tests. And just to acknowledge who made these waveguides, they're from Alex Zamait's group, now at the University of Rostock, and they write these by focusing a high-powered pulsed laser into quartz glass, dragging the glass along, and this creates a refractive index modification that localizes then light to point, and they can write arbitrary structure, and it works quite well. I guess the propagation loss is not too bad, but coupling in and out is quite bad. So in that sense, it's not so ideal. And so far also we didn't, I guess nowadays they can actually do phase shifters on top by thermo-optic, by heating basically. And I guess that's what we should have. Okay, and so we'll see how this goes. This is how the tritter works. As I said, by tunnel coupling, you send in light here, and it will then divide. If you stop the interaction zone at the right length, you can get the 1/3, 1/3, 1/3 coupling. Of course, this won't work anymore with more than 3 at the same time, because it would be impossible to arrange the coupling. If it's only a splitter, then it would be fine, but as a sort of symmetric unitary, it'd be difficult. And then you would have to subdivide it by Michael Rex Anton's technique into beam splitters and phase shifters. All right, and this is, again, I already said this, a steel wire that blocks the light from going through, and the light will mostly be reflected and scattered. yeah, this might actually be a problem. And this is how it looked in the lab. So there's an actual little servo motors that pull the wires up and down in these holes. Unfortunately, that doesn't always work so well, but so sometimes they get stuck. But in the end, we got some reasonable data. This is only with laser light though, and single photon detectors, and we see sort of values that, in fact, there's a bit of a systematic shift here, which we've basically localized or attributed to a phase crosstalk, meaning that if we have one wire up or down, either by mechanical stress or yeah, in fact, I don't know exactly what, it seems to influence the relative phase of the other paths. This is the problem now, of course, when we do this in a solid rather than in a free space interferometer, that there's more means of interaction, unwanted interaction between the parts. And in fact, we did try to, I'm not going to show this, to do this at different temperatures so that the phase could actually be changed in the chip a little bit, but find roughly the same values. Okay, and here's the conclusions. We really need phase control, individual phase control. The wire shutters, as I said, cause a small crosstalk, and crosstalk is exactly what we don't want. That's the worst kind of thing we can have in these experiments, because it's precisely about doing things to separate parts of the experiments that should not directly influence the other parts. Then another thing that will come up in a second is that, in fact, these wire shutters have some residual transmissivity. They will transmit something like 10 to the minus 4 of the incoming light somehow into the output. Not quite sure how this happens, and it's also not very reliable. So, and one reason also for doing this in the waveguides was to do the Paris test for quaternion quantum mechanics. And so, let me switch to this. I'm sure that most people here know what quaternions are. I did not know before we started this business. Quaternions are one of the few possible extensions of complex numbers to higher dimensions. In fact, there's not many. At least there's not many so-called normed division algebras where you can multiply and divide, and every step you go, you lose some property. And in this case, going from complex to quaternions, you lose commutativity. There's 3 imaginary units, I, j, and k. They all square to -1, and they are also anti-commuting, so that I times j is k and j times I is -k. So it's a 4-dimensional number field, or 4-dimensional algebra, introduced originally by Hamilton. And there's a whole book by Stephen Adler about quaternionic quantum mechanics. Some people here, Philip's not here, I guess, but Bori, and have also interacted with Stephen Adler, as have I at an earlier conference here in Vienna, and he already told me there it's a lost cause to look for quaternions, because he's proved that you cannot find them. They might be there, but you cannot find them in the far field. Okay, so nevertheless, we looked into this paper by Asher Paris, where he proposed that one could scatter, for example, neutrons at different scattering centers, and it turns out that if quantum mechanical amplitudes were represented by quaternion numbers rather than complex numbers, one might be able to find this out. How can one find this out? Well, you would try to measure the phase between the different amplitudes, and you can recover the phase between two vectors, of course, by the cosine law here, and we can basically measure the angle of this triangle by standard triangle arithmetic. And as you see here, we take the probability for 2 paths minus single, and then divide by this by the geometric mean of the probabilities, so the mean length. And then, of course, you realize this is pretty much exactly what we measured in the previous experiments, right? The same quantities. So why not try this? This is not yet a test here. This is just the phase between two vectors. And now you realize that it might depend on the space in which your amplitudes live. If they all live in the complex plane, then obviously three vectors will have angles that sum to 2 pi. Any three vectors in the complex plane will have to sum to 2 pi. But if you now go, imagine doing this on a sphere or in some higher dimensional space, then three vectors, their angles don't need to, well, I'm bad at pointing, but don't need to sum to 2 pi. As you will find if you walk around the Earth on the sphere, then the angles will in fact be larger inside a triangle. And so this is what Perez put into a quantity he called F. So all these cosines, the phase cosines between three amplitudes in an interferometer, alpha, beta, and gamma, can be put into an expression F. And it turns out that this quantity F will be equal to 1 if these vectors are coplanar, so for complex wave functions, and if psi is quaternion, or the vectors are non-coplanar, then F would be smaller or equal to 1. And he also points out already in this paper that there are some problems. And one of the problems is that this does not work for mixed states. It works, the Sorkin test is fine if the coherence is not perfect, it makes no change. But here, if coherence is not perfect, this will not work. And you can immediately see this if you just imagine that the phases here, for example, between these vectors all wiggle, then the sum of the average will not necessarily go to 2 pi. That's the problem. And it also then, of course, requires that the interferometer is perfect. And the free space interferometer is very difficult to get perfect mode matching so that this wave and that wave match perfectly. You can improve this by filtering, but this was sort of the prime reason to go to waveguides initially. And then it turns out, and this is something we did not know initially, unfortunately, it is very sensitive to imperfect shutters. So if you have some background that comes from the path that is currently blocked out, that can make a false positive. And so it turns out in our free space interferometer, we did the algebra, and the F was much smaller than 1, but we did not publish a discovery of quaternions for good reason. And so another thing that one should have is different types of phase shifts. In fact, in Philip's group's experiment, that's what they did, so that potentially you could access different, the different dimensions, an I and the J and the K. In Perez proposed different scattering of neutrons based on different forces or different materials. We could also imagine combining dynamic phases, tunnel phases, geometric phases, something like that in optics. But I think for now this is out of the question for the waveguides. And I also want to point out that so far this test had not been performed. At least we're not aware of any publication. But people did perform tests for non-commutativity. And so then the question of one referee to our recent paper came up: is there a difference even? Does it make a difference whether you test for this phase summing or for plain non-commutativity, for example, by swapping phase shifters or in a Sagnac interferometer? And maybe I'll go to this first and show that there was a neutron interferometry experiment where sort of the phase shifters here, titanium and aluminum, were swapped, and they found no effect within the precision of the experiment. And then in Philip's group, I already mentioned, 2007, the Sagnac interferometer, where also the two paths basically correspond to different orders of two different phase shifters, and they used a metamaterial negative index material for one of them. And so both basically concluded that there was no quaternion sign, no sign of quaternions up to a certain level. And now it turns out that the three-path test, of course, also depends on the commutativity in some sense, or it's not. Well, we haven't been able to prove that it's logically equivalent, so we claim it's something a bit different, but it's certainly related, because and one way of seeing this is that you can actually view a quaternion as a real, which is also sometimes called a scalar, plus a so-called vector part. So the imaginary parts you can combine into a three-dimensional vector. And it turns out that two quaternions commute if and only if the vector parts are collinear. Okay, something I didn't know, but you can find it on Wikipedia, and probably in some math books too. And then it turns out that if they commute, we can immediately prove that f will be equal to 1. Okay, so there will be no quaternion effects visible if you only work with commuting amplitudes, because then obviously also if they are collinear, then everything happens in a two-dimensional plane in quaternion space, and every two-dimensional plane that contains the real axis is equivalent to the complex numbers. And in the other direction, if f is equal 1, then we conclude that the amplitudes in the interferometer must be coplanar. And then if one of the amplitudes is real, then we also know that all of them that the vector parts are collinear and all the quaternions commute. So in that sense, the three-path test is perhaps not so much different from just the bare commutativity test, except that you sort of prove the mutual commutation of three amplitudes at the same time. All right. More I cannot really say, other than we still think it's an interesting experiment. All right, I already said this, and then we had our waveguide interferometer that I introduced, and now this plot looks very similar, but it has a different scale. So here is now f, the Perez quantity, and it should be 1 for complex numbers, and you see it's not 1, it's actually significantly below. Here's a histogram. The mean is at 0.95. And this uncertainty here is only the random uncertainty, so it doesn't include any systematic effects. And one of the referees was actually quite critical. It's now accepted, by the way. Okay. Thanks for your help. And made us think about this quite a bit, about non-commutativity and so. And it turns out now that when we analyzed why is this not 1, then it turns out that the main reason, and I don't want to go through all these numbers here, that the main problem is residual light. So this is light that goes through the shutters, and this is coherent light. So you have a small amplitude that kind of modulates what comes out of the two other paths, and that gives you a big deviation, like we see here, 10 to the minus 2. Now, can we somehow improve this? Let's look at what is the effect. It depends on the phase that this residual light has. You will see that it actually changes our quantity f by a number that varies from plus to minus with this phase. So if we had access to this phase, we could actually at least calibrate out the effect of this residual light. Unfortunately, in that waveguide interferometer, we had not. And so we could only put a rather weak bound on this quantity. And this is why already a while ago, we decided to go to a different interferometer. This is just summing up what I just said. We need phase control. Okay. And so this is what we're looking at, our latest interferometer. This is a cross section of waveguides. This is a commercial waveguides in silicon nitride, and now everything is done interferometrically. The downside is they cannot do an actual 3x3 coupler, because it's all planar, so you can only couple 2 waveguides ever. So now you have to construct the tritter by composing it of beam splitters. And it also turns out that the beam splitters have a relatively large tolerance for the coupling ratio. And if we want a very high precision interferometer, this means that every every interferometer has to consist of 3 interferometers, every Mach-Zehnder. And here's the idea. So this would be a single Mach-Zehnder interferometer, one coupler, a phase shift, and another coupler. And because the couplers are not very precise, we have to replace this coupler by an interferometer. And so an entire shutter, which is a very high precision interferometer now, consists of 3. And the first and the last are only used to make sure they act as 50-50 couplers, as good as possible. Okay, and the middle one is then the actual interferometer. If we tune this to 0, then all the light couples out there. If we tune this to pi, all the light goes out there. So we can basically move the light around. This, of course, complicates the entire structure. So to make a tritter where we don't care so much about the exact ratio, it looks like this. And then the entire chip looks like that. It has 18 phase shifters and as many, I guess, a few more couplers on it. And there's one big advantage. So now our shutter, in fact, also gives us the light that it blocks. So we have some outputs that are sort of the outputs of the interferometer, but of course, the light that we block is not really blocked, it's just routed to a different output, except for the middle one here, because there is no waveguide crossings, so we can actually not access the light there. And there's a light trap, something that's supposed to absorb everything, so that we don't, again, suffer from light that's not supposed to be anywhere in our output. All right, and now, of course, this takes actually took a while to realize. And again, we want to avoid crosstalk. So it turns out trenches are etched between these different phase shifters, so that operating one thermal phase shifter does not influence the other paths. But still, the size of the chip gives some limitation on the crosstalk, on the achievable crosstalk. And in the end, this is you can see it here. This is 8 by 32 millimeters, so 3 centimeters long is the chip. Yeah, and all the gold wires you see are basically the contacts to the heaters. Okay, and yeah, and this is very low loss, and I guess this is just too much detail. And what's interesting, at least to the experimentalists, is how well can we now actually block the light. And we find that we can block it depending on, it's not the same quality for all of them, to about 10 to the minus 5 level. So 10 to the minus 5 of the maximum transmitted amplitude is what comes out the dark port. And that's so far probably I don't even know yet whether it is limited by the detector noise or by the precision of the thermal control. So that's something we have to find out, whether this can still be made better. At least what's clear is that the interference itself is near perfect. So it's really single mode waveguides that are interacting here. And then we also found, unfortunately, that the crosstalk, meaning what happens if I operate shutter C or a shifter on C, what happens to the phase in A, unfortunately, is not so great. At least from A to B and from C to B, it seems to be at a 10 to the minus 3 level. And we've been thinking about schemes where we balance the total electrical power by not only manipulating the one phase shift and the shutter, but all 3. So that maybe the total electrical power or total deposited thermal power stays the same while changing the phase to reduce the effect on the remote ones. Okay, and this is the performance of the tritter. It's not so interesting. It's reasonably symmetric, in fact, not so important. And so now, what's the result? In fact, I don't have a proper result yet. This is basically the results. So that our f-1 for this is expected to be only maybe 1 or 2 orders of magnitude better, and hopefully with some improvements we can get it down. The residual light we might be able in this case to calibrate out by changing its phase. And then you can have a result where you say, okay, if I believe that this is an effect of the residual light, then my result is this good, and if I don't believe it, then my result is a bit worse. That's the thing, and that's the status of it. All right. So I guess that's about it, and I'm actually done anyways. I would just like to acknowledge now the people who did this. Mostly it's Robert Keil as a postdoc or senior scientist in my group, and Sebastian Gstiers, the PhD student. And I already pointed out the collaborations here with Czaslaw and Bori. In fact, I should put Bori separate here. And the waveguides from Alex Samite's group. And then also we're looking into doing this with multi-particle interference, which of course makes the measurements much, much harder and lengthier. And that's all. Thank you very much for your attention on the screens and in the hall.
Thank you, Gregor, very much. We have a question.
So for this Paris test, how do you distinguish, let's say, a setting with a quaternionic wave function from one with a spin 1/2 internal degree of freedom in ordinary complex mechanics? So basically a qubit is a quaternion, right? So so if your neutrons do have spin, right? So that is almost a quaternionic wave function after all. I mean, this stuff that I think Tony may be talking about that, where they distinguish against the reals, the meat is really in the locality conditions. Now, do you have a single particle? And for that, it seems you couldn't really tell a quaternionic system from one with an additional spin 1/2 degree of freedom.
In fact, thank you for the question, because we did in the past analyze what happens with photon polarization. Yeah? But I seem to remember, I don't have the algebra now in my head, that if we take care of actually using polarizers well enough, that an additional internal degree of freedom that I project out at the beginning and at the end in the middle couldn't actually do anything, but now I'm not so sure anymore. It's
I think I can also comment on this.
Your initial polarization. I mean, if you fix the polarization of your light initially in free space, let's say, that would be completely analogous to focusing only on multiples of the first quaternionic unit, something like that.
Right.
The constant and the first unit. So you have a single unit. You're basically effectively this is complex.
Right.
So that would be exactly the same thing.
Right, but then you could probably say, how well are you confined in sort of the spin degree of freedom, and
you're basically testing how well you can do the whole thing in linear polarization.
Right, exactly. And then if there's something beyond that, because if you fix the polarization at the beginning and at the end, then whatever happens in between, I don't know if that can really matter.
Okay.
I can also maybe comment on this. This you're completely right. So this is with internal degree of freedom, you can completely simulate quaternions. But then I think to which degree you can control polarization, right? Somehow. You believe that you know, okay? And then if something happens, then you know.
Yeah, I think that's what I meant.
In the same spirit, I guess. What is the shape of your channels written into the? Because this can have an influence on the polarization.
In fact, very very good point. These latest waveguides here are very asymmetric. In fact, they only guide one polarization. I think is the TM. To some degree, right? There's always some guiding for the other, but effectively it's a polarizing waveguide. You see that. So this is here. I don't know there's some reason why it needs two strips, but this is basically the core, very elongated in some other medium.
I have a cultural question.
Yes.
Why was the name of Hamilton cancelled on the photo that you showed?
Was it cancelled?
Yes. You can go to that plate there. The family name. There was that's why I recognized the word Hamilton is.
It's true. Somebody must have violated the thing. Didn't say. I will look into it.
More questions? Please. Oh, no. Okay, so I have a question. I think we discussed this all the time, but somehow to a certain extent you are doing calibration of your setup. You are trying somehow to get rid of all systematic errors, which is hard work. But is there any use, let's say, of these techniques to really do calibration? With this, can you see it? It's better than just a standard way. Should you do it for interferometers?
That's a very good question. So what I can say is that it turns out that this three-path thing is a really good way of showing nonlinearity, which has nothing to do with the calibration, but it's an extremely sensitive nonlinearity test if you believe that Born's rule or the square law in electrodynamics is correct. Now the crosstalk calibration or the calibration that we do here, in fact, I guess if you were to look for crosstalk, you would evaluate the same expressions that you also do for the Perez quantities. So these phase terms, in fact, crosstalk could be a problem, right? If you imagined operating some kind of unitary network for a photonic quantum computer, you also want to avoid crosstalk, I guess.
I understood that this is a kind of serious business that to get rid of in this chip business crosstalks. This is like a big problem.
Exactly, but then. But I guess the quantities that we measure are not different that anyone else would measure in that case. So because the Perez quantity builds on these separate phase cosines, those are the standard quantities that you would calculate. So in that sense, I haven't seen that it would add more. Whereas with the Sorkin test, I think that was something that people would not have looked at otherwise.
Can I ask a rather general question? I wonder to which extent your experiments are quantum. Because if I look at electrodynamics, electromagnetic superposition, we have the same laws. We're just not talking about psi, but the electric field. And there you could also ask whether there's an additional three term and all this kind of thing.
Exactly, and in fact, in our past experiments, we in fact tried to say that these are really separate experiments depending on how we do them. But then other people, and this goes a bit into Adler's direction, would argue that with photons this is not interesting in the first place. That you really would have to do this with massive particles. On the other hand, to find a violation of energy conservation in electrodynamics would probably be even worse or even more sensational than a quantum mechanical minor problem. So, because if we say that we find a violation of Born's rule here, this would mean with our low energy photons that somehow the energy density is not proportional to the square of the field.
I was asking, suppose you find something on a quantum level, how does the classical limit look like for that?
Yeah, I guess
if you have many photons and so on, we should.
Exactly. I mean, we do this with many photons and linear detectors, but then the underlying mechanism is the same. So I don't even know if they are really different experiments.
Energy conservation then.
Yeah, well, up to our systematic errors, a little bit, yeah.
Yeah, maybe just to refer to this, one can think about the toy models where you have a relation on the quantum level, nevertheless have the same classical limit. Of course, they are very strange and so on. But it's more of a personal question. I'm observing you and your group putting really huge effort to reduce the systematic errors. And whenever you see some deviation, you put more effort to do it. And you said you didn't want to publish this result of f smaller than 1. But at what point would you stop looking for the systematic errors? And maybe in that view, what is the next you expect from this research line?
I guess one of the things we get out of here, out of this last one, is how good can these waveguide interferometers be? Yeah? And then at some point you just have to either go for a new technology or stop it. And of course, then you publish whenever you have reached a better level, maybe one order of magnitude or so. But then
you have somehow in the back of your mind always the validity of quantum theory. That's why you are looking for the systematic errors all the time. Right. And you want to test it at the end.
Sure. But I guess if I don't find, so I think what's fascinating about it is really about finding these systematic errors, the things that you haven't thought about, and this happens to, I guess, in Marcus's experiments, in all of these experiments. What's the problem? And that in itself is, I mean, at least for us experimentalists, is kind of interesting. And then under the assumption that it's valid. So the question is, when would you say, okay, now we've exhausted all options, there must be something wrong with quantum? Yes, very good point. I think, as I said, I wasn't happy with the level of precision. So I don't know if in 10 years from now, if we still do this, I don't know, would I then be happy at the level of 10 to the minus 10? It's hard to say. It's like with when will we have a quantum computer, or what is a quantum computer? It's also a bit of a matter of taste, I guess.
But I guess you also want somehow, because other experiments that have put some limits on the let's say the potential deviation, so you want somehow also to improve on this, right? So
right. In fact, this is what I meant to say about the commutativity, and that we can make sort of a comparison between the commutativity tests and this 3-path interference. We can make a quantitative comparison, and in that sense, it looks for now on the raw data worse, but in fact with the phase scanning technique, it should be able to go into the same order of magnitude.
Okay, I think we should move on. Thank you, Gregor, once more.